Computer-aided manufacturing (CAM). In a world full of physical stuff, whether to manufacture a product or a part, computer-aided manufacturing (CAM) makes it all possible. We're the ones that give the power of flight to airplanes or the rumble of horsepower to automobiles. When something needs to be made, not just designed, CAM is there. Manufacturing module is used in PTC Creo for this purpose. CAM is the use of software and computer-controlled machinery to automate a manufacturing process. It stands for computer-aided manufacturing. Based on that definition, 3 components are required for a CAM system to function. A. Software that tells a machine how to make a product by generating toolpaths. B. Post-processing converts toolpaths into a language machine can understand. C. Machinery that can turn raw material into a finished product. These 3 components are glued together with tons of human labor and skill. Industries spent years building and refining the best manufacturing machinery around. Today, there's no design too tough for any capable machinist shop to handle. Without CAM, there is no CAD. CAD focuses on the design of a product or part, how it looks and how it functions. CAM focuses on how to make it. The start of every engineering process begins in the world of CAD. Engineers will make either a 2D or 3D drawing, whether that's a crankshaft for an automobile, the inner skeleton of a kitchen faucet, or the hidden electronics in a circuit board. In CAD, any design is called a model and contains a set of physical properties that will be used by a CAM system. Once CAD model is imported into CAM, the software starts preparing the model for machining. Machining is the controlled process of transforming raw material into a defined shape through actions like cutting, drilling, or boring. The example illustrates the sequence of tasks accompanied by CAD-CAM process. Computer-aided manufacturing software prepares a model for machining by working through several actions, including A. Checking if the model has any geometry errors that will impact the manufacturing process. B. Creating a toolpath for the model, a set of coordinates the machine will follow during the machining process. C. Setting any required machine parameters, including cutting speed, voltage, cut/pierce height, etc. D. Configuring nesting, where the CAM system will decide the best orientation for a part to maximize machining efficiency. The Creo NC user interface is ribbon-based and consists of tabs with groups of frequently used commands organized in a logical sequence. The group overflow area contains additional commands that are not frequently used. The ribbon display can be minimized or maximized by double-clicking on a tab or by right-clicking on the ribbon and clicking Minimize the ribbon on the shortcut menu. The commands on these tabs helps in setting up elements in a manufacturing process and enable systematic completion of tasks. For example, commands can be used on the NC tab to set up the manufacturing database items such as work cells, tools, and fixtures. After the database is set up, mill and turn NC sequences can be created to calculate and display toolpaths. Basic ribbon tabs are always available with the NC user interface, like manufacturing, model, analysis, annotate, render, tools, and applications. The following tabs are required for NC, and their availability is based on the current active operation and the machine tool or work center it references. Only one operation will be active at a time. Click Ribbon Manufacturing tab, Process Panel, Operation to activate the required operation. A mill. Available when the active operation references a mill or mill turn work center. B. Turn. Available when the active operation references a mill turn or lathe work center. C. Wire EDM. Available when the active operation references a wire EDM work center. Material is one of the tool parameters stored in tool directory. Creo NC places all the tool parameter files, .tpm files, in the /home/users/toolcrib directory. To set up the material directory structure, subdirectory in the tooling directory is created and named as materials. Further subdirectories are created corresponding to stock materials and conditions under the materials directory. For example, you can create subdirectories steel 20, steel 30, aluminum, and so on. Click File menu, Prepare, Model Properties, Material to assign material to the stock material or workpiece. Click Ribbon Manufacturing tab, Define Work Center, Turret/Fixture option in Work Center dialog box, Tools Setup, General, Material to assign material to the cutting tool. Cutting tool parameters for machining process can be specified by using relevant work center, lathe, mill, mill turn, wire cut EDM, user-defined, etc., and tool setup dialog box in Creo. In tool setup dialog box, various options related to tool parameters are specified like type of cutting tool, dimensions of cutting tool, spindle speed, tool movement direction, feed rate, axial depth, radial depth, coolant utilization, etc. Click Ribbon Manufacturing tab, Define Work Center, Turret/Fixture option in Work Center dialog box, Tools Setup to provide tool parameter. Strategy of cutting processes. Creo NC process consists of the following basic steps. A. Manufacturing database is created that includes various elements like machine tools availability, tooling, fixture configurations, site parameters, or tool tables. B. After creating manufacturing database, machine operation is defined. Primary elements involved in operation setup are work centers, tooling, and coordinate system. C. Creating NC sequences for the specified operation. Each NC sequence is a series of tool motions with the addition of specific post-processor words that are not motion-related but required for the correct NC output. The tool path is automatically generated by the system based on the NC sequence type, cut geometry, and manufacturing parameters. D. For each completed NC sequence, you can create a material removal feature, either by making the system automatically remove material, where applicable, or by manually constructing a regular Creo feature on the workpiece, such as slot or hole. The tool path is automatically generated by the system based on the NC sequence type, cut geometry, and manufacturing parameters. However, it can be manually created by using Operations tab. Let's discuss the method to generate tool path in bit details. A. Launch PTC Creo Parametric from desktop. Click ribbon New Manufacturing Module NC Assembly. Unselect Use Default Template and select the relevant template. Click OK. NC User Interface will open. B. Click ribbon Manufacturing tab to import CAD model of final part.prt to be manufactured into manufacturing module. Select the CAD file .prt and click Open. C. A Component Placement tab will open. Click on Default from List of Constraint Relationship Type. Verify if Status of Constraint turns into Fully Constrained on ribbon. Click green tick symbol as OK on ribbon. D. Click Ribbon Manufacturing tab, Components panel, Workpiece, Automatic Workpiece to assign stock material. Its dimensions must be similar to the material actually to be mounted on CNC milling. Select the type of workpiece such as rectangular for milling or circular for turning. Click Ribbon Options to specify the dimensions of stock material from X, Y, Z offsets. Click OK. E. Click Ribbon Manufacturing tab, Process Panel Operation. A window will open. Specify type of work center from manufacturing setup options such as mill. Specify the reference coordinate system for the current operation, such as milling from datum option, and place it above the workpiece. Provide 3 references for coordinate system such as top surface and 2 vertical planes surrounding the workpiece. Place it at x equals 0, y equals 0. Play the operation and select the created coordinate system from model tree. Click OK. F. Click Ribbon Manufacturing tab, Manufacturing Geometry panel, Mill window. Mill window interface will open. Select the top surface as mill window and click OK. H. Specify the roughing machining parameters. Specify the cutting tool to be used. Click References and select mill window from model tree. Click on Parameters to specify feed, spindle speed, step over, etc. Click on Clearance to specify tool clearance. Click on Display the tool path in Graphics window option. Play Path dialog box and Cutting tool will be displayed. H. Specify the roughing machining parameters. Specify the cutting tool to be used. Click References and select Mill window from model tree. Click on Parameters to specify feed, spindle speed, step over, etc. Click on Clearance to specify tool clearance. Click on Display the tool path in Graphics window option. Play Path dialog box and Cutting tool will be displayed. On Play Path dialog box, click on Play option. Tool path of cutting tool will be displayed. Click on CL data to review tool path in the form of computer language. On Play Path, click File, Save, as to save the toolpath in the form of CL data. The CL data in the form of .ncl format will be saved. Click OK. Roughing operation is now completed. For other operations, parameters will change, but the process will almost be same. Click Ribbon Manufacturing tab, Output Panel, post a CL file to convert computer language into a machine language, such as the language machine can understand. Select the already saved .ncl file. Select the compatible post process such as GSK, FANUC, etc. Now the file will be saved in .tap format. Open it with Notepad. CNC toolpath in the form of machine language will be displayed. K toolpath in machine language. Tool motion and a simulation can be displayed before creating a tool path to verify the tool path and make a visual check for interference with fixtures. Tool motion and tool simulation for existing tool paths and for whole operation can also be displayed. All simulated tool dimensions represent the parameters defined during tool setup. For this purpose, Play Path dialog box is used. The collapsible upper portion of this dialog box lists the cutter location, CL, data for the tool path or operation, as it would be output to a CL data file through Output, Create CL File. Click File, Save as to save the CL file in .ncl format to the desired location. The lower portion contains the following buttons: Play Forward, Play Back, Stop, Fast Forward to the end of the tool path, and Rewind to start of tool path, as well as Next CL Record and File and Previous CL Record and File. It also contains the buttons for positioning the cutting tool and for accessing the tool clearance functionality, and a slider to adjust the display speed. 2D Cam. Cutting out a part with features at the same depth such as in 2 dimensions is called 2D Cam. 2D Cam incorporates following operations: holes drilling, face cutting, side cutting, pocket cutting, and slot cutting. Holes drilling is a cutting process that uses a drill bit to cut a hole of circular cross-section in solid materials. The drill bit is usually a rotary cutting tool, often multi-point. The bit is pressed against the work piece and rotated at rates from hundreds to thousands of revolutions per minute. A holes drilling NC sequence is created by selecting the cycle type and specifying the holes to drill by defining the hole sets. The order of machining the holes is defined by the scan_type parameter value. A hole set includes one or more holes to be drilled. Each hole set has a drilling depth specification or countersink diameter value associated with it. You can include more than one hole set in a single hole making NC sequence. This allows drilling of holes with different depth specifications, as well as having multiple countersink diameter values within a single NC sequence. For milling, click Ribbon Mill tab, Hole Making Cycles, select desired tool to be used. Standard hole making using Play Path. The face cutting option allows to face down the workpiece with a flat or radius end mill. A planar surface or coplanar surfaces or a mill window parallel to the retract plane can be selected. All inner contours in the selected faces, holes, slots will be automatically excluded. The system will generate the appropriate tool path based on the selected surfaces. The example illustrates face cutting on planar surface. Use surface milling to mill horizontal or slanted surfaces. The selected surfaces must allow for a continuous tool path. The example illustrates side milling on flat surface. There are several methods of defining the cut and generating the tool path. A. From surface ISO lines. Mill the selected surfaces by following the surface UV lines. B. Projected cuts. Mill the selected surfaces by projecting their contours on the retract plane, creating a flat tool path in this plane, using the appropriate scan type, and then projecting this tool path back on the original surfaces. This method is available for 3-axis surface milling only. Pocketing can be used to finish mill after a rough volume operation, or for direct finishing. The surfaces selected must allow for a continuous tool path. The pocket may include horizontal, vertical, or slanted surfaces. The walls of the pocket will be milled as with profiling, the bottom surfaces in volume milling. The example illustrates pocket cutting by removing a volume at constant depth. Trajectory milling allows to sweep a tool along any user-defined trajectory. It can be used for milling horizontal slots, The shape of the tool must correspond to that of the slot. It can also be used for chamfer milling. Standard milling and drilling tools can be used for all types of trajectory milling, as well as sketch customized tools for 2- and 3-axis NC sequences. The example illustrates slot cutting. Cam milling is a type of subtractive machining process that removes material from a workpiece by using a spinning tool like an end mill to cut the stock material. By using specialized software to automate manufacturing on compatible machinery. CAM software takes part files created in a computer-aided design, CAD, software, and creates the code to control CNC machines to cut the part. CAM milling is classified into 2 groups: rough cutting, finish cutting. The roughing operation in CAM milling is primarily used to remove the bulk material and to approximately shape the workpiece towards the finished form. These NC sequence types are designed specifically for high-speed mold machining, and especially for machining imported, non-solid geometry. Roughing and re-roughing NC sequences can directly machine models containing facet data in STL format. Re-roughing NC sequences create tool paths to machine only the areas where a previous roughing or re-roughing sequence could not reach. Typically, they are performed with a smaller tool and machine the areas that the larger roughing cutter could not enter due to its size. They do not attempt to remove scallops left between the slices of the reference sequence. Z-level roughing toolpath quickly removes the unwanted material from the planar surface, specifically in the form of cavity. The machining process involves a series of passes in the Z direction at a specified depth. Material can be removed across the entire surface within a specific area. Parallel level contouring to generate 2-axis cutter paths for rough milling by removing material at equal depth in the form of slices as parallel planes. In plunge roughing, the cutting is performed at the end of the tool instead of at the periphery, such as cutting in axial direction on the specified surface. The flat roughing uses a pocket-out pattern to remove material from feature faces that are flat and parallel to the XY machining surface. This feature creates a rough cut at the edges or boundaries of reference model in specified shape, e.g., chamfer. Stepover is defined as the space between 2 passes of a tool on a specified surface, such as distance between 2 adjacent tool paths. If stepover cutter diameter equals roughing. B. If stepover cutter diameter equals finishing. In the current scenario, such as roughing, stepover will be greater than cutter diameter. Leads are toolpath operations where the tool plunges into the material outside of the profile required to cut. This allows to counter any unwanted artifacts such as tear out, chipping, or burning, positioned inside waste material and away from the final piece. Finishing cut ensures smooth surface of an object with minimized depth of cut, while stepover kept below cutter diameter. Parallel finishing passes are parallel in the XY plane and follow the surface in the Z direction. You can choose the angle as well as the stepover in the horizontal direction. The passes can be linked in a zigzag pattern or unidirectional. The Z-level finishing method slices the feature at various depths in Z-axis and then mills each slice at constant depth of cut along XY plane. Corner and pencil finishing is used to create a single trace toolpath to clean up corners that occur between non-tangential surfaces. It machines all corners that are difficult to machine using conventional tool parameters. ISO line finishing. This strategy uses the ISO line curves of a surface to mill the surface. These curves can be in the row direction or column direction. Radial toolpaths are created from the center of the part, such as point A toward the outer boundary. The spiral finishing strategy creates a spiral path which is projected down on a surface. It is most useful in round, relatively flat areas. The flowline toolpath creates a pattern of parallel cuts following the UV curves of the selected surface. This toolpath has simplified geometry selection. The flowline toolpath uses the UV lines of the selected surface to determine the general toolpath direction. Shows the UV lines for the given part using green and orange. The lines are perpendicular to each other. Between 2 curves calculates tool paths that are bounded by 2 curves. This finishing operation is used to control the shape of the toolpath over multiple surfaces by restricting the machining of the surface to be between the 2 specified curves such as AB and XY. The tool paths mill a feature in a series of offsets, starting from the first or start curve towards the second or end curve. Swarf Finishing strategy cuts with the side of the tool and works only on developable surfaces because the tool must be in contact with the surface for the whole cutting depth, removing any leftover swarf on the surface of workpiece. Cutting finishing. Step over is the distance the cutter moves over when finished machining. For a smooth, high-quality surface, the step over should typically be less than 20% of the diameter of the cutter. The larger the step over, the faster the job will be machined, but the surface finish will be rough. Step over is defined as the space between two passes of a tool on a specified surface, such as distance between two adjacent tool paths. If step over cutter diameter equals roughing. If step over cutter diameter equals finishing. In the current scenario, such as finishing, step over will be less than the cutter diameter. The cam lathe is an automatic machining process that controls the CNC lathe by a cam software-generated set of instructions in the form of a computer program. Process involved to implement cam lathe is similar as cam milling with some minor deviations like type of work center, tool setup, and machine operations. Cam lathe interface with defined parameters like work center, workpiece, tool setup, and turn profile. On Turn tab, Manufacturing Geometry panel, Turn Profile. Profile of turning can be defined. Turning tab incorporates different turning operations, while Hole Making Cycles tab includes different drilling options related to cam lathe. Cam lathe operations incorporates facing, boring, grooving, threading, and cutoff operations. Facing is an operation of machining the end of a workpiece perpendicular to the rotating axis. During the facing, the tool moves along the radius of the workpiece to produce the desired part length and a smooth face surface by removing a thin layer of material. The example illustrates facing operation. Click ribbon, turn tab, Hole Making Cycles panel, face for facing. Boring is the operation of enlarging the hole, which is already drilled, punched, or forged. It cannot produce a hole. It consists of a boring bar having a single-point cutting tool that enlarges the hole. It also corrects out of the roundness of a hole. The speed of this process is slow. The example illustrates boring operation. Click ribbon, turn tab, Hole Making Cycles panel, boring for this operation. Grooving, the process of reducing the diameter of a workpiece over a very narrow surface. It is done by a groove tool. A grooving tool is similar to the parting off tool. It is often done at the end of a thread or adjacent to a shoulder to leave a small margin. The example illustrates the grooving operation using grooving tool. Click ribbon, turn tab, turning panel, groove turning for grooving. When the threads or helical grooves are formed on the out surface of the workpiece is called external thread cutting. When the threads or helical grooves are formed on the inner surface of the workpiece is called internal thread cutting. The workpiece is rotating between the two centers such as live center and dead center of the lathe. The example illustrates threading operation. Click ribbon, turn tab, turning panel, thread turning for threading. Cutoff or parting is a machining operation that results in a part cut off at the end of the machining cycle. The process uses a tool with a specific shape to enter the workpiece perpendicular to the rotating axis and make a progressive cut while the workpiece rotates. After the edge of the cutting tool reaches the center of the workpiece drops off. The example illustrates parting operation using parting tool. Click ribbon, turn tab, turning panel, area turning for cutoff. Cam wire cut. Electrical discharge machining, EDM, is a metal fabrication process whereby a desired shape is obtained by a series of rapidly recurring current discharges between two electrodes, separated by a dielectric liquid and subject to an electric voltage. One of the electrodes is called the tool electrode at cathode, while the other is called the workpiece electrode at anode. The process depends upon the tool and workpiece not making physical contact. Cam wire cut operations incorporate die cutting, punch cutting, taper cutting, axis wiring cutting, and no-core cutting operations. Die sink EDM occurs when both the electrode such as workpiece and tool is submerged in light oil, acting as an insulator, where the constantly running dielectric fluid allows the temperature of the workpiece to be maintained. The dielectric fluid also causes vaporized hard material to be flushed out, bringing both the copper electrode, a conductive material, and metal workpiece within a small range apart. This causes a high-voltage spark to jump onto the workpiece from the electrode and discharging them between the closest points on the electrode and workpiece, which is the spark gap. The example illustrates die cutting operation. Punch cutting approach involves the use of a tool to punch a precisely shaped hole in the piece of material to be punched or drilled. The excess slugs removed from the material with each punch is recycled wherever possible. The term taper cutting is commonly used for generating parts with tapered profiles, for instance, tooling in which a draft angle is present. In this case, the angle is achieved by applying a relative movement between the upper and the lower guides. 4-axis wiring cutting. This EDM allows the two guides to move in different directions. For example, the upper guide may move in a circular motion while the lower guide moves in a square motion, ensuring a gradual transition between the shapes. No core cutting. In small-hole electrical discharge machining, a small diameter, usually hollow, spinning electrode is applied to a workpiece. It is known as EDM drilling or EDM micro-hole drilling around 0.025 millimeters. Small-hole EDM has been used to produce holes in fuel injectors, turbine blades, cutting tools, coolant holes, etc. Cam router feature prepares tool path for workpieces with a large range of materials such as wood cutting, MDF, medium density fiberboard, cutting, plastics cutting, foams milling, and metals cutting. It incorporates following operations: contouring, pocketing, engraving, chamfering, raster to vector translator, and nesting. Contouring a part means creating a fine finish on an irregular or uneven surface. Dissimilar to finishing a flat or even part, contouring involves the finishing of a rounded, curved, or otherwise uniquely shaped part by specifying tool paths in XY at various levels in Z direction for 3D contouring. Removing material at a large rate in the form of pocket volumes from the surface of material at a specified and constant depth is called pocketing. The example illustrates pocketing at constant depth of cut specifying toolpath also. Engrave machines along the contours with V-shaped chamfer tools. Select the profile with edges, sketches, or faces. The tip of the tool is used to create sharp edges on the cavity corners. Profile of the engrave is dependent on the shape of the cutting tool. The example illustrates engraving on wooden flat surface using engraving tool. Machinists use chamfers to ease otherwise sharp edges, both for safety and to prevent damage to the edges. A chamfer may sometimes be regarded as a type of bevel, and the terms are often used interchangeably. A raster file is made up of dots, pixels, while the vector file is made up of sequential lines or curves. It is difficult to utilize raster file into CAM. For this purpose, it is converted into vector file using different software like Aspire, Carve, etc. Nesting software takes a series of flat patterns of parts to be cut out of sheets or rolls of material and works out the best pattern, or nest, in order to combine as many parts on the material with the least amount of waste. It also optimizes the cutting path to take the shortest time and generates the NC, numerical control, code used to drive the CNC machine that will cut the material. Multi-axis CAM machining is a type of CNC-controlled machining process in which CAM software generates a computer program applicable for the cutting tool that can move in 4 directions, or more than 4 directions. 10.7. The cutting tool is controlled by computer numerical control, CNC. Multi-axis machining is highly complex when compared to 2- or 3-axis machining. Additional axes require added technology and more complex programming. Any number of axes over a 3-axis CNC machine is counted in multi-axis machining, such as 4, 5, 6, 10, 12. In practice, CNC machines have been developed with up to 12 axes. Usually, higher axis machines can produce better parts but drive up the cost significantly. 4-axis machining adds another axis to the 3-axis predecessor. However, the complexity of the parts is not increased significantly, and the workpiece is still stationary. These machines have a 4th rotary axis besides the standard 3-axis. The cutting tool can move in these 4 axes simultaneously without any readjustment. The axis structure is as follows. A. X-axis, moving from right to left of the work table. B. Y-axis, moving from top to bottom of the work table. C. Z-axis, moving the spindle up and down perpendicular to the work table. D. A-axis, a rotary axis which rotates the cutting tool along the x-axis. 4-axis milling has the ability to create angled features on a two-dimensional base, while price is the only factor that opposes it. 4-axis CNC milling are good when the project requires 2D applications of 3-axis cutting, along with a particular additional requirement such as engraving. 5-axis swarf milling is a type of surface milling which machines a series of surfaces by cutting with the side of the tool. It is a side-cutting process useful for parts with beveled edges and tapered walls. The tool path is calculated for a straight edge across the two edges that define the surface. As long as the face between those two edges is straight, swarf cut can be used to machine it. By default, swarf milling produces a slice-by-slice tool path, with the slice shape corresponding to the 5-axis geometry being machined. At any point on the tool path, the tool is positioned tangent to the surface being machined. You can change the default axis definitions, as desired, by specifying a series of axis directions at a number of points selected. The default axis directions correspond to the machine geometry. The axes follow the boundary edges of the surfaces, or follow the ruling lines of the surfaces that are ruled. Swarf milling supports tapered tools, as well as the regular, cylindrical ones. 5-axis index drilling process uses the same 3-axis control for the milling process, but the machining table has the ability to rotate in 2 additional directions. This allows a workpiece to be machined from all sides, which reduces the need for setups and cuts cost. It also improves the capabilities of the CNC machine, allowing for more complex features to be milled. Now, 5-axis indexed milling isn't to be confused with true 5-axis machining, which allows for continuous machining of all 3 axes and the 2 rotational axes. Also known as 3+2 machining, 5-axis index machining does not maintain continuous contact of the cutting tool and workpiece through all rotational axes. It does, however, share many of the same benefits as standard 5-axis machining, such as A. Dimensional stability due to fewer setups. B. Improved surface finish using shorter tooling. C. Lower cycle time to reduce cost. D. Greater feature capabilities due to compound angle positioning. In addition to supporting more complex geometries, 5-axis indexed milling can also improve finishes on non-orthogonal surfaces. 5-axis index machining is perfect for parts that don't require extreme contour controls like jigs, fixtures, housings, and other components frequently used in manufacturing.